Hello, welcome to Chapter 14, Part 2, Introduction to Waves. Let's start by looking at the properties of waves. So imagine doing a little demonstration like this. Suppose you have a rope that's attached to the wall or a tree or something over here, and every once in a while you give the rope a little flick of the wrist to create a pulse. What happens is that pulse, which is a wave, travels down the rope, and you can see it propagating from left to right. Now, one thing, if you look at this, it looks like the rope is actually moving to the right, but it's not. In fact, the material of the rope only moves up and down, and we can see this more clearly by looking at this animation right here. Imagine taking the rope and go continuously flicking your wrist up and down like this. This is kind of shown in slow motion here. So you're creating a sequence of pulses, and these pulses move down the rope like this. What's shown here on the rope are little, let's say, like beads attached to the rope. And look at there's a red bead here, 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 and here. And notice that if you watch one of those red beads, all the red bead does is go up and down. It does not move left or right. And this is the characteristic of what is called a transverse wave, which we will look at a little bit more in the next slide. But so what is actually moving then? If the material of the wave is actually not moving down, the rope, what is transferring? Well, what is actually transferring is energy. The other thing I'll point out here is you can see that we can define the wavelength of this wave as the distance between two consecutive peaks. And we'll talk more about the wavelength and period and frequency of the wave a little bit later. So our definition of a wave is a traveling disturbance through an elastic medium that transmits energy. So in this case, the rope is our elastic medium. And what an elastic medium means is that it's a material or a substance that is basically stretchy. And most materials are elastic. Remember, we looked at this earlier in the course when we talked about Young's modulus, and even materials as hard as diamond do have elastic properties. So waves can travel through pretty much anything. They can travel through a liquid, solid, or even gases. The disturbance is, in this case, it's a single pulse. In this example here, the disturbance is a whole sequence of pulses that are sent down the wave at regular intervals. Another example to show some of these features is when we think about waves in water. So if we think about a wave on the ocean or a lake that's moving, this is showing 3 different snapshots, and let's say there's something floating in the water right there. It might be a jellyfish or an empty bottle or something like that. What happens as the wave travels through is the object floating in the water just moves up and then comes back down to the water level. And the same can be said for all the water molecules. They are not moving with the wave. The wave moves through the material, which is very evident and easily seen up here in these examples. Waves can be characterized into 2 different types. One is called transverse and the other is called longitudinal. So in a transverse wave, the oscillations or the vibrations are perpendicular or transverse, those mean the same thing, to the direction of wave travel. So here's a couple examples. This is a spring or a slinky, and you can see the hand here is creating waves, but this is what we saw in the previous slide. The disturbance in the slinky is just going up and down. The wave is traveling left to right, and the disturbance is going vertically up and down, transverse to the direction. Here's our rope again that we saw in the last slide. Again, the waves are moving horizontally, but the material in the rope is moving up and down. It's not moving back and forth. Now, a different type of wave is called a longitudinal wave, and that's the case where the oscillations are in the same direction as which the wave travels. So again, taking our slinky here, it's easy to create a longitudinal wave by pressing or pulling on the slinky here to create a pulse. And you can see the region of compression here actually travels down the slinky. But again, the slinky material is just vibrating back and forth. The material of the slinky is not traveling with the wave. The wave is traveling through the slinky. The wave always travels through the medium. The medium does not travel with the wave. But the key thing here for a longitudinal wave, again, is that the material, the medium, is vibrating back and forth in the same direction, horizontal, as the wave travels. Another classic example of a longitudinal wave is a sound wave, which is the subject of part 2 of this lecture. So this is a tube here filled with air. So every one of these black dots represents a molecule of air. And this plunger here is moving back and forth and creating these compressions of sound waves. When it piles up, it looks like it's piling up the molecules in front of the piston when it moves to the right. And then we can see these compressions moving at the speed of sound through the material, through the air. But again, it's important to note that any given molecule is not traveling from left to right all the way across the tube. It's just going back and forth. So for example, take a look at, there's 3 molecules. There's one red one here, red there, and red there. Watch what happens as a wave travels through it. The molecule goes to the right, it snaps back to the left, and then it goes back to the right, and back to the left. It's not going anywhere. It's not moving down the tube. It's just vibrating or oscillating back and forth in the same horizontal direction as the wave is traveling. So this is another classic example of a longitudinal wave. Waves can also be classified as either mechanical waves or electromagnetic waves. And in this, in Physics 101, we are going to be talking only about mechanical waves. Mechanical waves travel through a physical medium, which is either a solid, a liquid, or a gas. So for example, if we wiggle a string, the string is the physical medium, all right? It's a solid material. It's an elastic material. A sound wave that we just saw, that travels through a gas. Typically, sound also travels through liquids and solids, but when we think about sound traveling through the air, that wave is traveling through the air itself, the gas of the air. And then ocean waves, of course, are waves that are traveling through a liquid. Electromagnetic waves are very different, and we're not going to study those in this course. They will be the topic of Physics 102, but interestingly, electromagnetic waves can travel through a vacuum. They don't need a medium to propagate through. So without any physical medium, this is a very different type of wave. And these waves are due to oscillating electric and magnetic fields. Again, though, this is not the subject of this chapter, so we won't be talking about electromagnetic waves at this point. All waves have certain characteristics that they share with each other. And so that's what we're going to look at here. So the 4 main characteristics of any wave are amplitude, wavelength, period, and frequency. So the amplitude of the wave, this is something that we saw in the previous chapter on oscillations. It's the maximum displacement from the equilibrium position. So if this is a picture or a snapshot of a rope that has waves traveling on it, this is the equilibrium position here, which would be the rope held tight, where it's not vibrating at all. So the amplitude is measured from the equilibrium position up to the top of this crest here. Or we could likewise measure it from here down to the trough for this particular wave. But it's wherever there's a maximum distance from equilibrium up to the top or bottom of a wave, that is the amplitude, and that is measured in meters. We already saw a little example of the wavelength. The wavelength is the distance between two peaks or two troughs. So in this example here, we would measure from one crest here to the adjacent crest here, and this distance is called the wavelength. And the wavelength is usually designated with the symbol lambda. This is the Greek lowercase lambda symbol. And wavelength is a distance, so it is measured in meters. The period of a wave is the length of time for one cycle to pass the same point. So if we look at this wave here, so this is, you can think of this as a rope, and we're wiggling one end of the rope, and we're making these wave pulses travel down the rope. If we were to, let's say, put our marker right here, and we were to measure when one peak comes, like right now we start our stopwatch, and then when the next peak reaches right now, we would stop the watch. That would be the amount of time for one complete cycle to pass by our marker there. And so that is what we mean by a period. And the unit of period is second because, of course, period is measured as a unit of time. The last characteristic here is the frequency of the wave. That's the number of wave cycles per second. And again, what we would do is we could pick a point, for example, with my pointer here, and what we would do is we would count how many of these peaks come by every second. All right, if this wave was moving really fast, like a sound wave, we might see several hundred peaks streak by during 1 second, and that would give us the frequency of the wave. So the units of frequency are cycles per second, and that is called a hertz, which is abbreviated uppercase H, lowercase z. And by the way, frequency and period, we saw this in the last chapter, have a reciprocal relationship. The frequency is equal to 1 over the period, t, and likewise, the period, t, is equal to 1 over f, 1 over the frequency. So the first thing we're going to talk about here is the speed of the wave velocity. The way to figure this out is actually quite easy. Remember that one wave cycle has a length of one wavelength. Okay, that's the definition of the wavelength. And we know that each cycle goes by in one period of time, and period is designated as the uppercase T. So remember from kinematics, the study of motion, that velocity of an object is equal to the distance it travels divided by the time it takes. So if we let our distance be one wavelength that the wave is going to move, then we know the period the time that takes is one period t. So the next thing we can do here is remember that period t is equal to 1 over the frequency. And so we have 1 over f down here in the denominator of our fraction. So this f comes up to the top, and we end up with our formula for wave velocity. Wave velocity is equal to the wavelength, lambda, of the wave times f, which is the frequency of the wave. So it's a very fundamental and simple relationship here between the speed of a wave, its wavelength, and its frequency. So let's look at an example. Ocean waves that are 2 meters tall hit the beach every 5 seconds. The distance between the waves is 40 meters. So 4 questions here. What is the amplitude of the wave? Well, the amplitude here would be the height of the wave. So that's 2 meters. What is the period of the wave? Well, we were told that the waves are hitting the beach every 5 seconds. So that's the period. T is equal to 5 seconds. What is the frequency? Well, remember the frequency of a wave is equal to 1 over the period. So it's 1 over 5 seconds, which is 0.2 hertz. And finally, what is the wave speed? Well, wave speed, v, is equal to lambda f. So lambda is the wavelength. So that's the distance between the waves. That's the distance between two peaks or ocean waves is 40 meters. So that's our wavelength, lambda. And our frequency, we just got that up here, is 0.2. And so 40 times 0.2 turns out to be, that should be, this is a typo here, that should be 8. I'll cover up the 0 point. That should be 8 meters per second is the speed of our wave there. So the superposition principle states that when two or more waves are present, the net amplitude is the sum of the individual amplitudes. In other words, when there are two or more waves present at the same time, all we have to do is add up the waves to get the resulting effect. So there's a couple ways we can look at this. These are actual photographs taken of two pulses traveling along a string. So wave 1 here is this pulse here, and it's moving to the right. Wave 2 is this pulse over here, and it's moving to the left. So you can see what happens is when these two waves actually overlap each other, notice the result is the amplitude is greater. And that's because we're adding the effects of wave 1 and wave 2 together to get a larger overall wave. But then what's kind of interesting here is what happens is these two waves, they basically pass through each other and they keep moving. So this is wave 1 now over here on the right, it's moving away to the right, and wave 2 is moving to the left. So these two waves, they basically briefly interact with each other here, but then they pass right through each other and keep traveling on their own ways. Another example, this illustration here kind of shows the effects of superposition in a little more detail. Let's suppose we have a triangular shaped wave here that's moving to the right at 1 meter per second, and over here we have a rectangular pulse shaped like this moving to the left at 1 meter per second. So what happens is as they approach each other at a second later, they've each moved 1 meter, so they just start to interact right here. They're just beginning to touch. Now notice when they overlap here, we can see the triangular wave here is basically sitting on top of this rectangular wave here. This is the superposition principle. Remember, we're adding this amplitude of this triangle here, we're adding that to the rectangle here to get this shape. And then as the triangular wave moves to the right and the rectangular wave moves to the left a little more, they start to overlap less. In fact, now the triangular wave is starting to go beyond where the rectangular wave is, and we see half of it is sticking out here. The other half is still on top of the rectangular wave. So by superposition, we have to keep adding those two together. But once a second later, once the triangular wave has moved to the right and the rectangular wave moved to the left, they are no longer overlapping, and notice they look exactly as they did up here, but they've switched positions now, because remember, this one is moving to the right and this one is moving to the left. The most important effect of superposition is called constructive and destructive interference. So constructive interference occurs when we have two waves that are in phase. And what we mean by in phase is that the peaks of both waves line up with time and with space too, and they're in the same position. And notice the troughs also line up. So what happens here, remember, by superposition, we have to add this to this. So when we add these together, we get a resultant wave with twice the amplitude of the individual waves. So if the amplitude here is A, the amplitude here is 2A, because we're adding this A to this A down here, and we're getting a stronger wave. So if this was a sound wave, we would basically have a louder sound right here as a result of this constructive interference. So we say that these two waves are interfering with each other constructively to produce a stronger wave. Now look what happens in this case. What if the two waves are out of phase? In other words, this crest aligns with this trough and vice versa. The trough up here aligns with the crest here. So when we add these two together, remember that crests are positive if we think of the amplitude being above this dotted line here, whereas down here the trough is a negative value. So when we add these two waves together, something very interesting happens. The two waves completely cancel each other out, and we're left with no wave at all. So this is called destructive interference. The two waves interfere with each other destructively such that no resulting wave exists anymore. And if these were two sound waves, individually they would be heard quite easily, and they would both be loud by themselves, but if we were to play them together like this out of phase, they would actually cancel each other and we would not hear anything. And this is a very fascinating phenomena that we're going to look at. We already saw in the previous chapter how the loudspeaker works. Remember, the loudspeaker has this speaker cone that vibrates back and forth and creates sound waves. So what we're going to do in this demonstration is we're going to have two speakers connected to a signal generator, and we are going to play the sound in these speakers for both in phase and out of phase. So let's watch that video right now. So we're going to do an experiment here to investigate the effects of interference with sound waves. So I've got two speakers here. These are two stereo speakers, and they're both connected to a signal generator back here, which is producing a tone of 600 hertz, which is 600 cycles per second. So that's the tone we're hearing right now. And I've got both of these speakers connected to the same source, and they're connected in phase. And what I mean by that is on the back of the speaker there's a red wire and a black wire, and so I've connected red to red and black to black so that the two speakers are in phase. So what we're hearing now is constructive interference. So if I point these two speakers directly at each other like this, we can still hear a very loud tone. Now listen what happens when I switch the wires so that I connect red to black and black to red. Now both speakers are still playing a loud tone individually, but when they're played together like this, they're 180 degrees out of phase. So in other words, we're hearing the effects of destructive interference right now, and the sound waves are basically canceling each other out. If I bring them back apart, you can probably hear the sound starts to get louder again as they don't interfere as easily when they're farther apart.